Geez, Charlie. I still don't understand it when two vectors don't meet at a right angle.
I'll show you, Ed. Give me some grid paper.
I didn't bring any. You said we didn't need it anymore.
Oh, yeah. Let me see if I can remember how we did that thing last time.
We've seen how to solve vector problems without using a grid. Two vectors, A and B, have magnitudes of 4 and 5 units. We were to find the resultant, and then its magnitude and direction. Using some tools we borrowed from trigonometry, we resolved both vectors into their components. The cosine ratio allowed us to find the horizontal components, and the sine ratio gave us the vertical components. Looking at the diagram, we can see what we're actually doing when we add the components of A and B to get the resultant's ordered pair. The horizontal components of both vectors, placed end to end and added together, equal the horizontal component of the resultant. And here, both vertical components placed end to end give us the vertical component of the resultant. So far in the series, most of the vectors we've used have represented velocity. For example, 340 kilometers per hour at 135 degrees, 12 knots due east, and 240 kilometers per hour west. But even an ordinary chair sitting on the floor is surrounded by vectors. There are forces trying to move it. While the force of gravity pulls it down, the floor pushes it up. Anything that pulls or pushes, whether up or down, left or right, forward or backward, is known as force. And since the push or pull of a force is directional, force is always expressed as a vector. The only reason the chair isn't moving is that the force vector pulling down is balanced by the force vector pushing up. So the two forces are equal and opposite, and the chair is in equilibrium. Hold a book above a desk. Now drop it. The force of gravity pulls the book, and it begins to fall toward the center of the earth at an ever-increasing velocity, until it meets a second force, the upward reaction force of the desk. When a force is applied to an object, there's always a change in velocity called acceleration. The word acceleration describes a change in velocity whether the object is speeding up or slowing down. When a skydiver jumps from an airplane, she encounters two forces. The force of gravity accelerates her toward the Earth. But as her velocity increases, the force of the air resistance begins to counteract her acceleration until both forces are balanced and the skydiver is at equilibrium. Her velocity is constant. However, equilibrium will be reached sooner if she uses her parachute. A mass hanging at the end of a rope experiences the downward pull of gravity, but it doesn't fall, because there's another force pulling it up, the force of tension in the rope. These two forces have the same magnitude, but their directions are opposite. The forces balance, and so the mass does not fall. Here, a mass is being held up by the tension in two ropes. Since, once again, the mass is not falling, all of the forces on it must be balanced. Somehow, the tension forces in the two ropes are exactly balancing the force of gravity. By sliding one of the tension vectors to the terminal point of the other and drawing the resultant, we can see that the resultant of the two tension vectors is equal and opposite to the downward force of gravity. Here is a sled with two people. Three people. They draw straws to see who'll pull, and as usual, Jim loses. There are three basic positions he might take for pulling: high, medium, and low. Is one of them better than the other two? To help him, we'll use vectors to find out. First, the high position. Jim's pulling force is a vector, and it can be resolved into its horizontal and vertical components. The horizontal component represents the forward pull on the sled, and the vertical component represents the lift force. We'll slide the lift vector over here, because this is where the lift force is actually applied. So, we can see that there's a lot of lift and very little horizontal pull. We'll call this Jim's hernia position. In the medium position, the lift is equal to the pull. Things are looking up. But now, Jim takes up the low position. It's obvious that he's putting most of his energy into pulling the sled forward instead of lifting it. Aha, this is more like it. By looking at the components of a force vector, we can determine the amount of effort that will be expended on useful work, and how much will be wasted. Jim and Pete have had enough and decide to go home. But Jim's car gets stuck. So now, instead of pulling, Jim's going to have to do some pushing. He's quite strong and can exert a force of 500 newtons. Remember, we measure the strength of a force in newtons. His arms are at an angle of 65 degrees from the horizontal. Let's see how efficient this position is. The horizontal component is 500 cosine 65 degrees, and the vertical is 500 sine 65 degrees. That's about 211 and 453 newtons respectively. So, when Jim pushes with 500 newtons of force at 65 degrees, only 211 newtons are actually used to move the car forward. And unfortunately for him, 453 newtons are completely wasted, pushing the car deeper into the snow. Definitely not the best position. So he tries 500 newtons at 20 degrees from the horizontal. The horizontal and vertical components are 470 and 171 newtons. By changing the angle from 65 to 20 degrees, the horizontal push increases to 470 newtons. And only 171 newtons are wasted, pushing the car down into the snow. So the low position gives Jim more than twice as much horizontal push.
We're stuck. It's your turn to push, Ed. No, Ed. Too much lift. Not enough horizontal push. Oh, no, Ed. Why can't you ever do anything right?
Sorry, Charlie.